Okay, everybody. It is Tuesday, the 16th of July. This is will be our ninth day of content, or our ninth day of material. And what we've been doing so far is we've been most recently been talking about um, different forms or different ions and different forms of atoms and elements. Ions are particularly important for one of the things that we're going to be exploring in this or tomorrow's lecture. For today's lecture, which I have the PowerPoint and PDF posted on Canvas, they're available now. Sorry for the delay. Um, we are going to be talking about states of matter. Now, before I get into this, one of the things that I wanted to mention is that tomorrow I'm going to have a pre-recorded lecture. So we won't have our regular 10 a.m. meeting time. I'll have a lecture that has been pre-recorded along with the PDF and PowerPoint as is custom. Those will be available later today. So if you want, you can go ahead and tackle those. I'll also have a quiz corresponding to I'll have a quiz that goes up today at 12 and closes at 2 tomorrow, and then another quiz that goes up today at 12 and closes at 2 the next day. Um, Now, just so we're all on the same page, I use the word quiz just because that's what Canvas identifies them as. But don't get hung up on that. So like I said, there will be no 10 a.m. meeting tomorrow. It's a pre-recorded lecture, so this will be an asynchronous course meeting. So kind of not a meeting, but a meeting in the sense that I'll provide you with the information. Okay. Um, and if anyone has questions about that, feel free to ask now, or that's the sort of question that people typically like to wait until the end of the class and they say, oh, I missed something in the first 5 minutes of class. So here we are, states of matter. We're going from chapter 4 to chapter 6. And we'll bounce around a little bit. You know, if you look back at what we've covered, we didn't cover really all of chapter 1, all of chapter 2, but we did cover all of chapter 4. So we have some kind of latitude and freedom within this. So we're going to be talking about states of matter. And states of matter, I think that for the most part, you have a good sense of what they are because, well, we've talked about them previously. Um, but any science class that you've pretty much ever taken, that's one of the first things that's brought up. There's solids, liquids, and gases. Cool. Now, what we're going to do in this conversation is we're going to take a little bit of a deeper dive. So, yeah, like I was saying, here's kind of, we started with chapter 1, went through chapter 4. Now we're going to 6, then we'll go to 5, 7, and 8. And that will be the arc of our semester. So well, yeah, we're halfway done. Now, one of the things that we talked about previously was molecule polarity. We talked about if a molecule had any sort of pull to it. And I alluded to, and I will always bring this up, and I'll say that, it's basically like you have a game of tug of war or a tug of war match. And if let's say that we have the Incredible Hulk over here. I should have drawn it. No, this is me. And now I can do what I intended to do. And I'm going to do a tug of war versus the Incredible Hulk. So I don't know if you know this, but when you're doing stick figures of the Incredible Hulk, you just make the Incredible Hulk's arms longer. So if myself and the Incredible Hulk were doing a tug of war match, well, it's pretty safe to say that the Incredible Hulk would win by it'd be pretty extreme. So the Incredible Hulk would win, and essentially he's pulling, giving a pull, Pole. to this game of tug of war. Now, that's one way that we can think about a compound. So, or think about a bond and then think about a molecule. If that molecule is asymmetric, me versus the Incredible Hulk is an asymmetric match of tug of war. Now, if this was now here's Hulk versus Hulk over here. If it's Hulk versus Hulk in a match of tug of war, and I didn't draw them green because it just takes a little bit of extra time to swap out the colors. But that's worth it. Here, Incredible Hulk versus Incredible Hulk. Well, then they're going to be pulling with equal forces, in which case, well, that match of tug of war is basically going to go nowhere. And so this is a symmetric molecule. This is a symmetric match of tug of war. Right? Now, we previously talked about, and I think any chemistry class that you've ever taken, you've talked about solids, liquids, and gases, and you can see it and say, aha, there we go. That's a solid. This is a liquid. And this is a gas. Oh, there's something in it. Oh, that's kind of like is the glass half empty or half full? Well, the glass is completely full with a liquid in the bottom half and then a gas in the top half. And that's a really good joke to help you really quickly lose friends. Um, because it's not wrong, but it's just kind of like, oh, okay, now it's not a high quality joke ultimately. Um, but my point is that we have a liquid, a solid, and a gas. These pictures up here are their macro states. Down here are their micro. When we look at these solids, liquids, and gases at the molecular or the atomic level, these are the differences that we see. One of the things that I want you to notice is in the lower left-hand corner of each one of these, there is basically a counter. And this counter is counting up. And it's rated in FS or femtoseconds. So on the far left, you can see the ever slightest bit of motion and movement within that solid. And it's true. There is the slightest bit of motion and movement between the molecules that make up a solid, but the motion is extremely small and it's very brief. Now, liquid, by contrast, like if we tracked, if you were able to kind of keep your eye on, okay, that's the one that I want to watch. Oh, well, it moved over here, moved over here. Okay, I'm tracking one of these balls corresponding to one of the molecules of a liquid. It's going to move from point A to point B in this time frame. Whereas our solid, okay, that molecule that I just drew a dot over, going to move from point A, and I'm going to watch it for 10 days, and it's going to stay at point A. Then we watch a gas, and just kind of pick one of these balls. Say, okay, nope, that one's off the screen. Okay, what about this one? Oh, it's off the screen. What about, let's start from the right-hand side. I'm going to try, no. And I'm going to try to, there we go, there we go, there we go. Okay, cool, it's off the screen. The point is that the motion of the molecules or the particles of a solid, liquid, and a gas, they have motion. Gases are moving so much faster than liquids. Liquids are moving so much faster than solids. The rate of their motions are tremendously different from one another. A gas moves very quickly. In addition to that, if you compare the space between the molecules or the atoms or the particles of a gas, the space between them, okay, here we picked like they're basically the collisions. If you watch this box right here, if you slowed this down enough, you could probably count up the total number of collisions between all of the atoms and be able to say something like, oh, there are, 275 collisions in this, 36,000 femtoseconds. So 275 collisions. And I'm going to answer total. So one molecule hitting another one. And so on. I'm just picking a number that's like you could count it up. Now let's compare that to the liquids. First of all, the number of molecules that make up this liquid that are in this confined space is so much higher than the gas that if you wanted to count those collisions, I mean, heck, you watch these and it's like bump, 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 bump. You're gonna hit 275, and you really will not have even moved from, this small square. So then you're scaling it up. Okay, well, there were 500 in this time frame. 500, 500. We're talking about thousands upon thousands of collisions. And then if you look at the solids basically are in constant, the collisions between those, they're almost in constant contact. So it would almost be like an infinite number of collisions are taking place there. So what I want you to think about with respect to this is the spacing between the molecules and the number of collisions that they can possibly have. Okay. So the spacing is probably the biggest thing that I want you to take away from this. The space between molecules and atoms of a solid versus molecules and atoms of a liquid versus molecules and atoms of a gas. The space is so much greater in a gas than a liquid. The liquid is greater than the solid. Now, all of these things give rise to some of the properties that we already know. Solids have a fixed shape and a fixed volume. Liquids have a variable shape. Whatever container you put them in, they will take that shape. But a liquid sample is going to have a fixed volume. A gas will have a variable shape and a variable volume. If you put a gas into a container that is, as big as this solo cup here, well, it's going to fill that space and it's going to fill that shape. Whereas if you flatten this cup down, the volume doesn't change, but the shape changes. Now, what we're going to do here is we're going to look at how temperature can influence our states of matter. Okay, so here what we have is neon gas. Neon is a noble gas. As a noble gas, that is just each one of these atoms of neon has a complete octet. So it's in good shape, it's happy. Now, what we're going to do is we've got our temperature in Kelvin. What we are going to do is we're going to heat this solution up. As we add more heat, we've bumped it to 18 Kelvin. It's going to go from here what we have is we have this neon sample that, would you agree that this has a shape? Yeah. I mean, it's not really a square, but there is some sort of there are straight lines to it. There is some rigidity. This is a shape. Okay. So this shape is going to have a fixed volume. So we've got a fixed volume and a fixed shape. So this is a solid. Now let's heat this up. What's going to happen is that the amount of space between all of our molecules is going to increase, or between all of our atoms is going to increase as we increase the heat. As we increase the heat, the number of collisions is going to go up. We're going to see this transition from a solid where there is limited, sorry, a kind of fixed shape and a fixed volume. Then we're going to go to a liquid where, okay, yeah, there are some collisions and the shape is a little bit different, to gas where it's almost complete chaos. Now, argon is basically going to go the same way because argon is also a noble gas. So what we have taking place here is all of these individual elements, or all of these individual atoms of neon or argon, they're still making collisions and everything like that. As a solid, they're super rigid. Now let's go on to something that is a diatomic element, like oxygen. Can oxygen exist as a solid? It can. At what temperature will oxygen exist as a solid? Well, at negative 246 degrees Celsius. So at an extremely low temperature, oxygen can exist as a solid. Well, can oxygen exist as a liquid? Yes, it can. It's going to exist as a liquid at approximately negative 216 degrees Celsius. Can oxygen exist as a gas? It better, at negative 160 degrees Celsius. So one thing that I want you to recognize about this is that regardless of the state of oxygen, whether it's a solid, a liquid, or a gas, the two red balls that constitute oxygen, those are remaining intact. They are remaining as a complete thing. Now, let's look at water. Okay, water as a solid, ice. Okay, negative 127 degrees Celsius. Liquid water. Okay, this is at 13 degrees Celsius. Okay, so, you know, there's definitely more motion. There's a shape. It's basically sunk to the bottom. As a gas, water's floating around. Yeah, that's steam. So what I want you to take away from this is really doubling down on what we saw in the previous slides, where we were looking at how the motion between our different, um, the motion and the space between our molecules and atoms, it increases as temperature increases. It decreases as temperature decreases. Now, there we primarily focused on um, temperature, and what we can also do is we could also look at how pressure influences this. So let's say that we've got, okay, I'm going to go back to states and we're going to go with water. And just because this is a little bit more of a tangible, I'm going to heat this water up to 5 degrees Celsius. So this solid water to 5 degrees Celsius. So this is definitely a liquid. Now, 5 degrees Celsius is approximately like probably 45 to 47 degrees Fahrenheit. So definitely a chilly day. You can have liquid water there. That liquid, you don't have to worry about if you have water in a cup and you walk outside and it's, 47 degrees Celsius, you don't have to worry about it evaporating. However, what happens whenever we increase the pressure? Sorry. So we're depressing this, so we're putting more pressure into the system. As we increase the pressure, oh, popped off. I just did a pressure cooker essentially. I'm gonna return my lid there. So let's drop my temperature a little bit. I'm going back to that 5 degrees Celsius. So now what I'm going to do is increase the pressure. And look at that. I increased my pressure. And what happened was my temperature went way up. So under higher pressure, my temperature increases. And what do you notice about all of the different molecules of my water? Well, the motion of all of them increased dramatically. Now, did the space increase? Well, not really, because I limited the space that they could have. So what I did was I took something at a low temperature, I increased the pressure. That causes the number of collisions to go higher, increase very dramatically, and my temperature went up as well. So the point here, the takeaway from this is that pressure and temperature have an impact on the state of matter. Now, this diagram right here, this graph is a graph that I want you to be very familiar with. We're going to look at this graph through basically, or by basically only looking at um, water, or we're going to focus primarily on water for our study of this graph. This is what is known as a phase diagram. Now, whenever you look at a graph where you've got a y-axis and an x-axis, you want to see what those labels are. So this y-axis has a range from 0 to infinity. These are positive numbers. So 1, 2, 3, and so on. So we see an increase in temperature on my y-axis. On my x-axis, we're seeing an increasing energy content of a sample. So what that means is that the energy that is present in our sample with all of those different collisions taking place, that's going to be increasing. So if we increase the temperature, what does that mean? That means that we increase the number and frequency of collisions between all the different atoms. Okay, so that's our y-axis versus our x-axis. Now, if we have, okay, so let's start at this origin. If we're increasing the temperature of our sample of ice, we have solid ice that's going to warm, and then at some point, it's going to melt. So let's say that we had ice that was at negative 80 degrees Celsius. Okay. If it's at negative 75 degrees Celsius, still ice. Negative 70, still ice. Negative 65, still ice. It's going to still be ice. It's still going to exist as a solid until we hit 0 degrees Celsius. Now, one thing that I think everyone's familiar with is if you have ice at exactly 32 degrees Fahrenheit or at exactly 0 degrees Celsius, what do you notice about that? Well, it doesn't spontaneously turn into a liquid because what we have to have is this, what's known as a phase change, where we're transitioning. So this right here, we are transitioning from a solid to a liquid. Okay, that solid to liquid transition is known as melting. Okay, then whenever we have that liquid, we continue heating it up and we're going to hit our boiling point, which is 100 degrees Celsius. Water doesn't spontaneously turn to gas at 100 degrees Celsius because we have all of that liquid that has to undergo that transition. And that transition, which is depicted by this horizontal line right here, is our liquid to gas. So when you look at a phase diagram like this, you should have two horizontal regions. And those represent phase changes. Now, when we're going from a solid to a liquid, that is known as melting. Going from a liquid to a gas, that is known as vaporization. Water becomes water vapor, hence vaporization. Now, if we look at these in the opposite direction, when I'm going to change colors over here, a gas goes to a liquid, that's in a process known as condensation. Liquid goes to a solid, that is through a process known as freezing. These are phase changes, but it's just the direction. Liquid to gas is vaporization, gas to liquid is condensation. Liquid to solid is freezing. This is another phase diagram. So this demonstrates phase changes. This diagram shows our phase changes. This diagram shows a basically the coordinates on our y and x axis for our pressure and temperature, where our different substances are going to exist, or the state that a substance is going to exist in. So for example, a phase diagram like this will show which temperature and pressure something exists as a solid, which temperature and pressure something exists as a liquid, something exists as a gas, and then where something exists as a supercritical fluid. So a supercritical fluid is something that's kind of a mixture of a liquid and a gas. Now we're going to focus on solids and liquids. So if we were to pick a pressure right here, let's just call this 15 pressure. And then let's go ahead and say at 5 degrees Celsius, then 15 degrees Celsius, then 35 degrees Celsius. If our pressure is 15 and our temperature is 5 degrees Celsius, our sample will exist as a solid. If we heat it up from 5 to 15 degrees Celsius, but hold the pressure constant, well, then our sample is going to exist as a liquid. If we continue heating our sample to approximately 35 degrees Celsius, then our sample is going to exist as a gas. So if your pressure remains constant, it's entirely possible that your sample will transition from a solid to a liquid to a gas, all depending on the temperature. Now, if you drop this sample down to 5 pressure, then at 5 degrees Celsius, it's solid. 15, it's a gas. And 35, it's also a gas. If you go up to, let's say, 35, and I'm just kind of arbitrary, I'm just kind of picking these numbers at random. 35 pressure and 5 degrees Celsius, a solid. At 15 degrees Celsius, it's a solid. At 35 degrees Celsius, ooh, that's right there. It's probably going to be a liquid, or could be a supercritical fluid. Um, but it's important that you know how to read these, because this also shows if we have a, if you apply enough pressure to something. So if your pressure continues to go up, what we were seeing earlier, oh wait, that's on that webpage. I'm gonna go ahead and switch my share. We're increasing the, here in this demonstration, it's about to pop off, yep. But here we've got water, and if we cool it down, we're talking, this is at 1,000 degrees Celsius, 970 degrees Celsius. If I cool this down, and then I increase my pressure, my temperature is going up, and ultimately it's getting closer to being like a solid, which, if you think about, here, there we go, we got it reset. I'm increasing the collisions. I'm basically trying to trap all of these molecules into a limited space so that they have a strict range that they can move in. And so arguably they look more like a solid. So this is similar to what you see, or sorry, there's, um, can you think of something that is formed under extreme pressure and is a solid? Diamonds. Diamonds under extremely high levels of pressure, and basically they're just confined and compact until that solid, that very strong solid, is formed. Now, what we can do is we can use this information here for knowledge of our phase changes and apply it to movement or movements on a phase diagram like this. So which process is indicated by this arrow? We're going from a solid to a liquid. Any solid going to a liquid is going to melt. Doesn't matter if it's ice going to water, could be, well, yeah, any solid going to a liquid. Sodium at a certain temperature will melt. Which process is indicated by the arrow going from a gas to a liquid? Ooh, gas to a liquid, that is condensation. Now, what we're going to be looking at now is something that we'll again revisit in our next lecture, but that is intra and intermolecular forces. The intermolecular forces are forces between molecules. Intramolecular forces is something that we've talked about a little bit more. A covalent bond, for example, is an intramolecular force because this is within a single molecule. Sort of, whenever I hear intermolecular forces, so that I can keep this straight, I always think of the interstate highway system. The interstate highway system is a highway system that goes between states. So Interstate 35 can drive you from Minnesota all the way to Central Texas, or any part of Texas, really, for that matter. But those Texas and Minnesota are different states. Now, sorry, we have ionic and molecular substances. So an ionic solid has strong electrostatic interactions, whereas a molecular solid has weak intermolecular forces. So electrostatic interactions are strong forces that hold a sodium ion here and a chloride ion in close contact to one another. Now, CH4, this is NaCl, this is CH4. Well, this is CH4, this is CH4, this is CH4, this is CH4. These are held together through weak intermolecular forces. This whole thing is held together through electrostatic interactions. These individual CH4 molecules are held together by intramolecular forces, known as covalent bonds. Now, an ionic substance like NaCl, and I think that it's good just to have one to kind of hang your hat on, is going to be a solid at room temperature. It's going to have a very high melting point and a high boiling point, and it's going to conduct electricity when it's a liquid. Now, this is something that's always kind of tricky. Like if you go to your kitchen and you get some sodium chloride, and then you add it to some water, you'll see it disappear. And that is not melting. That is dissolving, that is dissociating. The sodium ion and chloride ion, they are separating from one another. If, however, you got sodium chloride, and let's say that you just decided to put it into a frying pan and put that frying pan on your range oven, and you increase the heat of that, or you increase the heat to, maximum level on your iron, or on your, sorry, on your range oven. That NaCl is going to probably what's going to happen is it's going to pop. And that NaCl, because those little crystals are going to pop and one of them is going to spray. So that's very dangerous. Do not do that. But a conventional oven in your kitchen or something like that will not get the temperature high enough for that solid NaCl to melt. However, is it possible to get NaCl to melt? Yes, it is. If you had basically an industrial strength or an industrial oven or something like that, yeah, you could get NaCl to melt. Could you get it to make a gas? Yeah, you could. In fact, let's see. The NaCl melting point is 1,474 degrees Celsius. The boiling point is 2,669 degrees Celsius. So NaCl, simple table salt, will melt if you heat it to 1,479 degrees Celsius. And if you then boil it, or if you heat it to 2,669, then it's going to form a gas. So sodium chloride as an ionic compound is very strong. That's how much heat you have to put into it. Compare that to a molecular substance. You have a gas, liquid, or a solid at room temperature. These are going to have low melting and low boiling points. These are not going to conduct electricity when they're liquid. So these are the biggest differences. An example of a molecular substance would be something like sugar. C6H12O6. Now, which solid is likely to require the greatest input to melt? Okay, we've got sodium fluoride, an ionic compound, ice, H2O, dry ice, CO2, sucrose. Okay, so I always like to try to think of, have I seen this before? Could I make this something tangible? If you got an ice cube and you put it on the range oven or on your stove, is it eventually going to melt? Yeah, you could probably do that without even adjusting the thermostat or adjusting the dial. Now, dry ice. You got dry ice and you put it on your stove. Could it melt? Yep, again, without even adjusting the stove. So those two are out. Now we're between sucrose and sodium fluoride. Well, sucrose, sugar, or a sugar, and sodium fluoride, an ionic compound. Essentially, if you got table sugar, if you got sugar from, a bag at the grocery store, and you threw it into, um, let's just put it directly into a frying pan, and you heated it up, what's going to happen? This is going to caramelize. Now, caramelize is a food term, not exactly a chemical term or anything like that, but essentially, it's going to burn, it's going to melt. It's going to no longer look like this right here. It's effectively going to change. Now, that's because all of these are molecular compounds. Whereas sodium fluoride is an ionic compound. Ionic compounds are very, very strong. You're not going to see that change. You're going to see that continue to exist as a solid until you get to something like 1200 degrees Celsius. So A is going to require the greatest input of energy in order to get something to melt. In addition to that, ionic compounds are able to conduct electricity. Here what we have is sodium chloride, a salt water solution where we have an electric current running through it. Then we also have methanol. Sodium chloride is able to conduct electricity, whereas this methanol is not able to conduct electricity very well. Solute consists of molecules and no ions, whereas sodium chloride, well, those are positively and negatively charged species. So basically, your electrons can bounce between each one of these and basically form a current or sustain a current between those two electrodes. All right, and this is just kind of a nice little demonstration where you play around with sugar and salt solutions, and you can test whether or not it conducts electricity. Spoiler alert, salt will, sugar won't. Okay, well, I'm going to go ahead and stop the recording right there.